These are the quantification of energy exchange notes. I'll let you read what you need to read, and we will move down to the first problem. The first problem is based on this statement that the heat lost by this block of metal is gained by the water. So if we take the mass of the metal, we do not know the specific heat of the metal, but we do know the temperature change. It started at 55 degrees C, and both of them reached thermal equilibrium at 27 degrees. That means that the metal and the water were the same temperature. We can set that equal to the mass of the water times the specific heat of water times the temperature that the water changed. So we can do that right now. If we find that the mass of the metal times our x, which is the specific heat, the final temperature is 27 degrees, the initial temperature of the metal is 55. We can set that equal to the mass of the water times the specific heat of the water times the final temperature, 27, and the water started out at 25 degrees C. When we do our math, we come out with x equal to 0.957 joules grams degrees C. You may have noticed that you would get a negative sign. Let's remember that a specific heat is not a negative number, and we recall that we are using a positive and negative sign in any thermodynamic work to show the direction of flow only. Right, moving on to the second problem. It says a 100-gram sample of metal was heated to 100 degrees C and then quickly transferred into an insulated container holding 100 grams of water at 22 degrees C. The temperature of the water rose to a final temperature of 35 degrees C. Which of the following can be concluded? The metal temperature changed more than the water temperature did, therefore the metal lost more thermal energy than the water gained. Well, we just proved in the previous problem that the energy lost by the metal is gained by the water, so that means that A must be a false statement. The metal temperature changed more than the water temperature did. That is correct. But the metal lost the same amount of thermal energy as the heat gained. That is also a true statement. The difference between the metal and the water is their respective specific heat capacities. The metal temperature changed more than the water temperature did. Therefore, the heat capacity of the metal must be greater than the heat capacity of the water, when in fact the opposite is true. Water has a higher heat capacity than the metal does. That's why its temperature is resistant to change. The final temperature is less than the average starting temperature of the metal and the water. Therefore, the total energy of the metal and water is decreased. I don't even know. So the answer then is B. Moving down to our next problem. You are reading along and taking what you need from these notes. All right. So we have problem D. Calculate the delta H ought reaction. Okay, this is a lot of information. The change in enthalpy of the entire reaction when the entire reaction is at standard conditions. Standard conditions would be 25 degrees C, 1 atm, and all solutions would have a concentration of 1 molar. Okay, the big thing that you need to recall is delta H is equal to the sum of the individual enthalpies of the products minus the reactants. So, and we remember that all of these are per mole, So if you have a coefficient, you take the per molar and multiply it by the coefficient. This means there are 3 moles of NO. So to set this problem up, we would have negative 1676 plus negative 703, and it's a little jagged, sorry, plus 3 times 90 plus quantity 6 times negative 242. That would be the products, and from that we would subtract the reactants, 3 times 0. Remember that the enthalpy of formation of any element, including diatomic elements, is 0, plus 3 times a negative 295. And when I do my math, that means that the sum of the products is a negative 3,561 kilojoules minus the sum of the enthalpy of the reactants, and that is a negative 885 kilojoules, and that gives us the answer, negative 2676 kilojoules. And we rounded that up to 2680 to follow our Sig Fig rules. That means that when this reaction runs, 2680 kilojoules is released from the system, which would be this, to the surroundings. I'm going to move past these. These seem fairly elemental. And I'm going to go then to our next set of problems. And that would be a coffee cup calorimeter problem. Problem B. I'll let you read problem on your own. We'll start out with a balanced chemical reaction. We have added a base, NaOH, and mixed it with an acid, HCl, and together this neutralization reaction forms a salt and water. And there is the balanced reaction, right? And they tell us, please find the enthalpy change for this reaction. So we're going to find the delta H of this reaction. Alrighty, so we know a few things. First of all, Q equals MCAT is what we need to solve this. The mass of the solution is not given, but we do...
Leah Sutherland, please come to the AP office. Leah Sutherland, please come to the AP office.
But we do know that we can find the density divided by the volume will give us the mass. So if density equals mass over volume, then mass is equal to density divided by volume. So the density of the solution is 1, and we're looking for the mass, and the total volume of this solution is 200 milliliters. Therefore, the mass of this solution is 200.0 grams. So our mass is equal to 200.0 grams. The specific heat we will use for our solution is that of water, 4.18 joules, grams, degrees C. And our change in temperature will be our final temperature, which is 31.3 minus our initial temperature, which is 24.6, that will give us our heat of reaction. Remember, when there's no pressure change, the heat of reaction is equal to Q. So the heat of reaction is 56.05